Got to keep rolling through section 1.5, and then we'll answer some homework questions. What's scary?
Your videos are like black and white.
Oh yeah. That's the old style. That's why I switched. I started my channel over again. Okay. Finding an equation for F inverse. Let's just do the simple stuff here. 1, switch x and y. Can we do that? X equals y divided by y plus 1. Now there's a lot of you out there in TV land that struggle with knowing how to find or solve for y, right? How do we solve for y? Cancel what? Oh my goodness! Take the knife out now.
No, because that equals 0.
Ouch! Ouch! Folks, those are not factors which are cancelable because of the addition. All right. So, let's try again. Folks, it is a proportion. How do we handle proportions? Cross multiply. Thank you very much. That's what we're going to do. So let's see. We're going to multiply those. Y plus 1. Then we're going to multiply these, which is just good old y. Next on the list is something you do not do to minors. You want to do this only to people over the age of 18. Distribute. Thank you very much. All right, so when we distribute, we get what? Yeah, you get in trouble if you do that to minors. Ugh. You don't want to do that. Exactly. No illegal activity here. Man, we just distribute it. All right, now. Folks, if you want to get y by itself, back in pre-algebra days, they taught you that you needed to get the y terms on the same side. Those are actually called variable terms. Now, I know some of you are going to try to argue, well, what do you mean, Mr. Staley? They look all like variable terms to me. The ones that are called variable terms are the ones that have a y, because that's the variable you're solving for. I know. Pretty cool. So, what do you do to get all the y terms to the same side? Not yet. And I don't think that would be, I don't think that's advisable yet, so, I mean, at all, because you want y to be by itself. We want to subtract that term to the other side, right? So now we have x equals y minus xy. Now we have all the y terms on the same side. What are you going to do with those? Why don't you take the y out? I mean, not to dinner, folks, but just take it out. What are you left with? Something minus x. What is the first part? 1. 1 minus x, right? You're using the distributive property backwards. And now for our last trick to get x or y by itself, what are we going to do? Divide by 1 minus x. And that is how you get y by itself. Yeah, we had to cross multiply, we had to distribute, we had to get the y terms on the same side. Most of you probably, I mean, I have a lot of kids that they get lost in this process. Okay? But you're really just cross multiplying. You're following a lot of the same things you've done in your Algebra 1 days. Yeah, you got to look here and you got to pull out, you got to use the distributive property backwards and pull out the common factor. We did that in Algebra 2. But that gets you your inverse. But that's the process of finding the inverse. Yes. Y equals x over 1 minus x. That's your inverse. Now, if you want to be really cool, you would write f inverse of x equals x over 1 minus x. That would be the really cool way to do it. You know? -1, not like a 7. So I'm not going to require that you use the little F inverse notation. I'll be just happy that you cross multiplied and did all that algebra. Is what I'm going to be happy with. Okay. So one of the things that we talked about last year when we did this is that inverses are reflections. Do you remember what line they are reflected across? Yes, sir? Ooh, we got a winner. Nice job. All right. So the line y equals x. I'm going to try to do the best job I can here to get y equals x. Not the worst thing I've ever done. When we reflect this across that line, what's going to happen to this green dot? When we reflect that across the red line, y equals x, what's going to happen to the green dot? You got about 20 seconds to talk to your neighbors and figure out what's going to happen to that green dot. Go. What is, the approximate coordinate there is -1, -1. What's going to happen to that green dot? Nothing. Its x and y value are already the same. So, if you switch them, big deal. All right, now what's going to happen with this chunk down here? It's going to be reflected across on the other side. What's going to happen to the point 0, 1? Zero, 1. What's going to happen to that one? 1, 0, right? So you're going to do something like this. You need to be able to draw even draw a dotted line. Every point. I was doing this earlier with Algebra 2 kids. I will, sure. You just have to draw a picture that has a matching image on the other side. So look at this, because I did this earlier with some students. We were dealing with this, -x squared plus 3. Parabola, the red one, opens down. It was shifted up 3 units. So I made a big deal out of these 2 dots right here that I circled in green. And I asked them the same question I asked you. What's going to happen to those 2 points? Answer, nothing. The point 03 became the point 30, and then we had enough information to draw the shape. but it looked like a reflection across that line, a matching point on either side. It's not a rotation, folks. This is not a rotation. It's a reflection. So, I don't know, so for those of you who are looking at this picture, it's not like it does this. That's not what's going on here. What is going on? That. Right? This part's coming up, this part's coming over. It's reflecting. Is the original function 1-to-1? Now, what is that? Remind me what that means again. It has to, there's two criteria. Did we talk about this already? It has to pass both the vertical line test and the horizontal line test. Yeah, we talked about this yesterday. Because we kept saying things like, yeet. I don't think I wanted to start that over again, but I guess I did. So is the blue graph a 1-to-1 function? Yes or no? Yes or no? It sure does. It passes both of them, the vertical and the horizontal. I'm just talking about the blue one. I'm not saying we put the green one and the blue one together, because ain't no way you're passing that stuff if you're going to put them both on there. That's not what they're referring to. They're asking you if the original function is a 1-to-1. Okay. Talked a little bit about this last year. Need to do more with it this year. Composition of functions. A lot of you don't understand what this definition is saying. We've got two functions. Okay, first of all, we're starting off with a 1-to-1 function. All right, that's kind of important. Actually, that's extremely important. F of g of x is equal to x. Now, a lot of you don't even know what you're looking at when you see this happening. What are those two functions doing to each other? Okay, I'll give you a simple illustration. Every morning when I wake up, my feet are naked. I know. I put socks on. I go throughout the day. At the end of the day, I take the socks back off. Once again, my feet are naked. True story. Started out with naked feet, performed an operation, then I performed another operation, undid that one, ended up with the exact same thing, possibly a little bit more smelly, than what I started with. The definition says you have two functions, and what did they do to the original x? They canceled themselves out and left you with exactly what you started with. No matter which way you do the composition, you started with x, you better end up with x. If you start with x and end up with x plus 2, not inverses. You have to start with x and end up with x. You can bank money. There's a question on the test that's going to ask you whether two functions are inverses of each other. And I'm not going to let you switch x and y and solve for y. It'll say, use compositions only. So you better be able to do it. So let's see here. F of g of x. The one on the outside is the one that controls what's going on according to this. What does it tell me to do to everything I put into it? It looks like it says raise it to the third power and add 1. Does that make sense? Raise it to the third power and add 1? If it doesn't, now would be a good time to... What are we plugging in? Are we plugging in this other function? All right, cube root x minus 1. We typically refer to that as the unsimplified form, so why don't we find the simplified form? What happens to the cube and the cube root? They cancel out. So I have x minus 1 plus 1, commonly referred to on the street as x, right? Because these cancel, right? All right, so that one worked. G of f of x. What does the g function, the one on the outside, tell me to do to everything I plug into it? Cube root of something minus 1. Oh, back up here, folks, those parentheses were useful because the cube and the cube root canceled each other out. I forgot to say that. I don't know why I did. What's going to go inside here? What are we putting in here? X cubed plus 1. Are those parentheses useful or useless? They are useless. Nothing's going to be done with them, so you can pretty much ignore them, right? Gone. Anything simplify? We got a plus 1 and a minus 1. So now I have the cube root of x cubed, which gives me x. Oh, look, we got exactly what we started with, no matter which one we did. Now, one of my favorite things in the whole wide world was this term verifying. When you were in college and they said things like, verify that this is this. Guess what? They told you the answer. You just had to prove it. You just had to show them that it worked. You already knew these were going to be inverses. I'm going to give you two functions and say, are these two inverses? And then you're going to have to go through the process of solving both these compositions. If either one of them ends up being something else, the answer is no. I copied this from the book because I thought it was important to look at here. Some functions are so important that we need to study their inverses even though they are not one-to-one. A good example is the square root function, which is the inverse of the square function. It is not the inverse of the entire squaring function, because the full parabola fails the horizontal line test. Right here you can see that we're dealing with fails the horizontal line test. It's not one-to-one. Therefore, its inverse is not a function. Okay, but look over here at these two. Now, describe to me what's the domain of this function here. This y equals the square root of x. What's the domain? 0 to infinity, right? You know what? I think this is going to be a bad example because I don't think you're going to be able to see the difference. And how about range? Also the same thing, isn't it? Okay, this is why this is not going to illustrate what I wanted. Okay, go on ahead. All right, we'll see if this will help you. All right, so how do we find an inverse? We switch x and y, right? X equals the square root of y. What do we do to both sides to get the y by itself? We square both sides, right? And so most of you would say, oh, Mr. Staley, it's y equals x squared. What does y equals x squared look like? It's a parabola, right? Except not in this case. Why not? You started with this, right? Got this positive square root thing going on. You switch x and y in the equation. How the heck do you end up with this as your inverse? You created like a whole lot of points that don't exist. If you start with this, the only thing you're going to end up with is this. Correct. But the algebra that we just did has a limitation, and the limitation is that we didn't start with the full, this range right here. What happens when you switch x and y? What happens to these two things? What happens to the domain and range when you switch x and y? They switch, don't they? Now. All right, now. The problem that you don't see in this example is that I'm looking at one where the domain and range are exactly the same. That's why I didn't like this example so much. Maybe if we shifted it up 5 or something like that, it would be more obvious. Okay? But the domains and ranges switch. Now, which one of these is important to this? Which one? What's the domain of this? It's got to be one of those. Which one is it? It's the range. The range of the original is the domain of this one. Now, I know, they're exactly the same. But I need you to understand that there's a connection between the range of this and the domain of this. That's why it says that the square root of x is the inverse function of y equals x squared on the restricted domain 0 to pi. Now, what I'm trying to describe to you is what's called an inherited domain. You got the domain from the previous function. Here's your original. It was only this thing right here. Whatever the range of this thing is, that's going to be the domain of this thing. You can't just create points that don't exist. Which is why I tell a lot of you, it's kind of important that you know what the original picture looks like so that you can graph the inverse. Now, it's true that if you start with something like this, you're going to end up with something like this, and don't ask me why it doesn't do stuff like that. I don't know. It should. I know that's a picky detail, but it's called the inherited domain. So the range of this becomes the domain of the other one. So when they use that phrase, inherited domain, that's what if you were looking at the homework and it was asking for inherited domain, you saw on the calendar that I said we will have that discussion about inherited domain in class. You're getting the new domain from the old range, basically. So what does this picture look like? Positive square root of x plus 3. Well, we know what a positive square root looks like. What is the plus 3 doing to the whole thing? What number do you have to plug in there to get 0 to come out of it? Negative 3. Ding, ding, ding. Guess what? You just figured out that it went left 3. What? Okay, so that's what this is doing, left. What's the domain? -3 to infinity. What's the range? 0 to infinity, right? Smash it all on the y-axis and see what you get. Before we do the algebra, I need to know if this is a one-to-one function. Is this a one-to-one function? Sure is. So we definitely got the one-to-one part. You know, why not abbreviate it? Seriously. 1 to 1. Check. All right, passes horizontal and vertical. Line tests. We know that y equals x is doing something like this. What do we know about that red dot right there? What's going to happen when we reflect it? Stays the same. Kind of beat that pointer to the ground, sorry. So here, what's this coordinate over here? 3 units left of the origin. -3, 0. Okay, so where does that point go on the new graph? 0, -3, right? So hopefully you get the idea in your mind that you're doing this. What's the domain of the red one? What's the inherited domain of the red one? What did it get from the other one? It got 0 to infinity, right? With a range of obviously -3 to infinity. Yes, they just switched. Question? Yep. If you're switching x and y, then those domains and ranges are always going to switch. Which is why it's really important to know what the original one looks like. Otherwise, you're never going to know what the new one has. Because the algebra can be a tad bit misleading, like the one with the x squared. All right, so switch x and y. We got x equals the square root of y plus 3. Hopefully we know what to do with this. What do you do to get rid of the square root? Square it. Now what? Subtract 3, right? So we have x squared minus 3. As long as you have the correct domain, we're okay. It's not a complete parabola. It's only half. Because of that inherited domain. Yes, sir. Yeah. Where did I? Oh, there they are. I was like, I thought I had a bunch of them. Throw that out. Okay. Homework questions that you want to go over. Things you did not understand. Yep. Sorry. You're on. Number 6. Okay. Do you have another one? 6 and 19.
Can you also do 15?
Sure, but I'm like, what happened to my... Share. 6 and 15. Those are the ones I heard. And if there was another one, you'll have to tell me. Okay, why is that? They did an update on my program here. Okay, so 6. Not bad. What part of 6? Is it plugging in the numbers? Making the table? Okay, so do you know how to use your calculator in parametric mode?
Yeah.
Okay, so is it the part B where you're connecting y and x together? Is that the part?
Yeah.
Okay, so you've got to pick one of those equations to solve for t. I think 6, the first one, is the easiest one to solve, and you get 1 minus x. So what are we going to do with this in the other one? We're going to substitute, right? So we got something squared minus 2 times something. All right, and we're substituting in here and here. 1 minus x, 1 minus x. And FOIL however you like, whether you like the box or you hate the box. If you like FOIL, just writing parentheses side by side, it makes no difference to me. So I get x squared and a minus 2x and a plus 1, and then of course if I distribute that, I get, minus 2 and a plus x. So I end up with y equals x squared minus 1x minus 1 as my final. Now, did I do anything in there that kind of got weird or difficult? Okay. Just combine like terms after I did my multiplication. So no more t. That's basically what they're asking for in part B, is find a direct relationship where there's no t involved, no parametric form. And I'm sure you're capable of using your calculator to graph. So 15 was next on the list. Was there another one? I'm sorry, was there another hand up here besides the one that gave me 15? I know you said 15, right? Okay. What does that thing look like? 2x minus 3 over x plus 1. Better switch my calculator back to function instead of parametric so I can graph this thing. Otherwise, I'm going to get real frustrated. 2x minus 3 and x plus 1. What do we know from the denominator, x plus 1? What? Something happened at negative 1? What's happening at negative 1? Something, either an asymptote or something. What do you think? What do we get from the denominators? If it's an asymptote, what kind is it? Yeah, but is it a horizontal or is it a vertical? Definitely vertical. All right, so we got this picture. And you guys said that negative 1 was causing me a problem. True. All right, so what's the domain of that? What's the domain? Should be fast. Should be easy. Hey, guess what? Negative infinity's over here. Positive infinity's over there. Negative infinity to what? Negative 1 union. Negative 1 to infinity. Okay, what's the range? I really need you to figure out the range right now. Let me use my eraser. eraser and erase that. You need to figure out the range. Now, I taught you in these rational situations what to do. You needed to take the largest power of x in the top and the largest power of x in the bottom. And what's that going to give you? If we're using that little trick that we talked about for these rational functions, whoops, gotta actually have the writing tool on. 2x is the highest power of x in the top, 1x is the highest power of x in the bottom, and you reduce that, what are you looking for? Yes, you're looking for something to cancel or reduce. So it does, right? The x's disappear, you get 2. What is that we're finding? Horizontal asymptote, isn't it? Because that's the end behavior. That's what's going on far to the right and far to the left of the graph. So we just figured out that 2 is a horizontal asymptote. So tell me the range. Negative infinity to 2. Union 2 to infinity, right? Okay. Now we need to find a formula. So we switch x and y. X equals 2y minus 3 over y plus 1. Now what? Now what? Cross multiply. Excellent. Somebody paid attention to the first example we did. Nice. So we got x times y plus 1 equals 2y minus 3. All right. Now what? Distribute. xy plus x equals 2y minus 3. Name every single variable term up here. Name any term up here that you think is a variable term. xy, yes. Name another one that's a variable term. There's only one more. 2y. Now, why do we call those two variable terms? Because they have the y. And that's what you're trying to figure out, right? That's what you're trying to solve for. So don't we have to have those two terms on the same side and everything else on the other? Okay. Now what? What do you want to subtract? xy? Okay, we can subtract the xy. What are we going to do with the negative 3? We're going to add it, right? So if we do that, we would have x plus 3 equals 2y minus xy. So we got all of our y's on the same side. What can we do with this? Take out a y. I mean, not like with a contracted killer, but you know. Okay, we'll let that one sink in. All right, now what do we do? How do we get y by itself? Divide. Divide by 2 minus x. There's your inverse. What is the domain of that inverse? What is the domain of that? Negative infinity to what? Positive 2 union. Man, where'd you get that from? Ah, the range of the previous one, right? That's the inherited domain. That's what you got from the other one. Okay, finish up 27 through 32. And we'll be moving into 1-6 tomorrow. I'm looking at a test over 1-4 to 1-6 probably like Tuesday next week. Tuesday next week will be game day. I'm pretty sure. Tuesday or Wednesday, but I'm pretty sure it's going to be Tuesday. If you need to stop by and get resource room passes or get help from me, please do so soon.
I just had a question.